Hi everybody, today we are going to talk about the graphs of polar equations. So one way you can graph a polar equation is by using Tchart. So here we have r equals 4 times the sine of theta. So let's make a Tchart where we're going to pick different values for theta and find the r value. So let's start with 0. The sine of 0 is 0. How about pi over 6? The sine of pi over 6 is 1/2, so that gives us 2. We can do pi over 3, which is root 3 over 2, times 4 is 2 root 3. Let's do pi over 2. The sine of pi over 2 is 1, so we have 4. A few values on the other side. Let's do 2 pi over 3. Remember, sine is still positive in quadrant 2, so we have 2 root 3 again. Let's do 5 pi over 6, so that should also give us 2. And let's do pi, which brings us back to 0. Let's just do a couple more values. Let's do 3 pi over 2. And the sine of 3 pi over 2 is -1, so we have -4. And let's just do 11 pi over 6, and this should give us a -2. Okay, so let's go and plot these points. So I can see that our largest r value is 4, so I'm going to draw 4 rings on my graph. Now, in terms of the angles, we're just going to estimate the best we can. We know that, pi over 6 would be somewhere around here, pi over 4 is here, pi over 3 is here, so on and so forth. So let's start plotting. So we have 0, 0. Then we have pi over 6, 2, so let's call it right here. Then we have pi over 3, 2 root 3, and 2 root 3 is somewhere between 3 and 4, so let's say right around here. And then we have pi over 2, 4. And then plot those last couple points. And then we can see that we're back at pi 0. Now let's talk about these two, because we have that -r value. I want to remind you that with polar coordinates, a -r value does not mean to the left or down always. What it does mean is opposite direction. So 3 pi over 2 is right here. But I'm not moving 4 in this direction. I'm actually going to move 4 in the opposite direction. So that actually brings us back to this point, which we've already plotted, which is pi over 2, positive 4. Let's look at this point. 11 pi over 6 would be right here, but we're going to move 2 in the opposite direction, so it brings us to a point that we already have. So actually, for all the angles in quadrants 3 and 4, we're just repeating points that we already have. So if you look at this, you can tell that it actually makes a graph of a circle. So if I connect it, we get something like this. Now, of course, for this graph, we kind of estimated where those different angles are, but if you had a more accurate graph, this would be a pretty accurate circle. Now, of course, this can be kind of time consuming, and maybe with just the points we plotted, you wouldn't be able to tell exactly what type of curve this is. So luckily, there is a list of tricks that we can use to kind of guide us in this process. So here is a list of tricks that you can use to help you graph polar equations. So when I have a polar equation, the first thing I'm going to check for is the symmetry. So we're going to be working with two types, sine and cosine. So if you have a sine equation, you know that the graph is going to be symmetric with respect to the line theta equals pi over 2, which used to be what we called the y-axis. And if you have a cosine equation, it's going to be symmetric with respect to the polar axis, which is what we used to refer to as the x-axis. So after you know the symmetric properties of your graph, then what you're going to do is you're going to look for the form your equation is in. So one form that your equation can be in looks like this. We have a plus or minus b times sine or cosine of theta. Now here, this is going to be the only form where you see a constant. So these are called limitones, and they look kind of like circles. They're a little bit ovular, but you can see here that sometimes they kind of dip in. So there's 4 types. You have an inner loop, what's called a cardioid, you have a dimpled lemniscate, and you have a convex lemniscate. So the way you determine which type you have is by testing the ratio of A over B. And this is going to be absolute value for all of them. So if the absolute value of A over B is less than 1, you're going to have this little inner loop. So you can find a more accurate graph by plugging in a few points, but you should expect to have this inner loop, and that can guide you when you're making your curve. Now, if the ratio of A over B is exactly 1, your lemniscate is actually going to come to a point and loop around, and it's called a cardioid because it does kind of look like a heart. If your graph or the ratio is between 1 and 2, you kind of have this dimple. It still comes in, but it's curved. And then if it's greater than 2, the bigger it gets, the more convex your lemniscate gets. The next form that you're going to be looking for is when you have A times cosine of n theta or A times sine of n theta. So notice that not only do we have a coefficient, but now theta has a coefficient. So these make really, really cool looking graphs. They're called rose curves. So once again, you have to check for symmetry, and then you look at that n value. So if n is odd, that number is going to determine how many petals you have. These little loops are called petals. And if n is even, you're going to have twice as many petals as your n value. So if you look at this graph, I see 4 petals, which means my n value must have been 2. Here I see 5 petals, which means my n value must have been 5. Now, another thing to note, you can always plug in a few points to see where your graph should start and where your petals will fall, but the petals are always going to be evenly spaced. And for cosine, it's essentially going to start on your polar axis, but watch out for negatives. And for sine, it's essentially going to start somewhere in quadrant 1. And then you just have to match it for the symmetry and for the number of petals. Oh, another thing to note, that A value, the coefficient, is going to essentially tell you the length of your petal. And it will also determine how many rings you should draw on your graph. All right, the last 2 types are called, well, circles, which we already know, and lemniscates. So we just actually graphed this A times sine of theta. So if you see just A cosine or A sine of theta, you know it's just going to be a circle, and A is actually the length of your diameter. Cosine is going to fall on the right side, sine is going to fall on the top of your graph, and of course you can adjust it for negatives. Now this last type of curve, lemniscate, this one is going to really stand out because it's the only curve that has r squared in the equation. So if you see something like this, your curve is going to make this infinity shape, and it's always going to say 2 theta or cosine of 2 theta or sine of 2 theta, so you don't have to worry about that. But you do need to understand where your curve is going to fall. For sine, this is the only graph that really doesn't follow that symmetric property that we talked about. And that's because we have this r squared, meaning that our r value is always going to be positive. So even when we have angles down here, we're going to actually move out in this direction rather than moving in the opposite direction like we did in the previous example. I also want to point out that this formula, this value is a squared. So remember, to find a, you're going to have to take the square root. And then cosine is going to fall right on your polar axis. All right, let's give one of these a try. So looking at the form of your equation, we can tell that this curve is going to be a lemniscate, and it's going to be reflective over the polar axis because it is has cosine. Now the next thing we need to do is check the ratio of A over B. So I can see that that ratio is 3 over 2, which means that we are going to have a dimpled lemniscate. So to continue on here, we are going to want to plot or find a few points using a Tchart. Since we know that our graph is reflected over what's essentially the x-axis, we only want to really use angles in quadrants 1 and 2, and then we can just use those points and reflect them into quadrants 3 and 4, just to save us some time and to be more efficient. So let's go through the process. When we have 0, the cosine of 0 is 1, so we have 5. I'm going to pick pi over 3 because I know the cosine of pi over 3 is a nice number. It's 1/2. So this will give us a value of 4. And then let's do pi over 2. Cosine of pi over 2 is 0, so that leaves us with 3. Let's do 2 pi over 3. Remember, cosine becomes negative in quadrant 2, so we essentially have 3 plus -1, so it becomes 2. And then let's also do pi, so it becomes -1. 3 minus 2 is 1. So we can plot these points and then reflect them to make our entire graph. So let's give ourselves 5 rings because our largest R value is 5. Okay, and let's start plotting. So we have 5, 0, which is right here. Then we have 4 pi over 3, which could be around here. And then we have pi over 2, 3, 2 pi over 3, 2, and then pi 1. Now I'm going to reflect this point over my polar axis. So right here, I'm going to reflect this point here, and our last point is on the polar axis, so we don't have to worry about it. And what you, knowing that it should be a dimpled limosone, we can kind of make sure that our points match what our graph is supposed to look like. All right, why don't you go ahead and pause the video and give this problem a try. Please note that this time we have a sine equation, so it means that it's going to be reflected over the line theta equals pi over 2. So when you're plugging in points, make sure to only use points or angles in quadrant 1 or 4. Okay, so you can see that I found these points. I'll highlight them in red. I found these points in quadrants 1 and 4, and then I was able to reflect them over the line theta equals pi over 2. And I did know that this was supposed to be a dimpled limosone, so the points do match up with what we expected our curve to look like. Okay, let's try another one together. Here, again, we can see that we're going to have a limosone that is reflected over the polar axis. When we check the ratio of A over B, we can see that it's going to be, well, it's -1/2. The ratio, the absolute value of the ratio is 1/2. And since it's negative, that's going to tell us that our graph is actually going to be on the left side of our axis rather than the right side, but we can see that with our T-chart. But since the absolute value of A over B is less than 1, we know that this is going to have an inner loop. So we can definitely expect that in our graph. All right, now let's make a T-chart so we can get some of our values from quadrant 1 and 2. And then we'll just reflect it over the polar axis. Oops, sorry about that. So let's start with 0. The cosine of 0 is 1, so we have 1 minus 2, which is -1. So right off the bat, we can see that this coordinate, 0 is usually on the right, but since we're moving in the opposite direction, it's going to bring us to the left side of our equation. And then let's do pi over 3. So we're going to have 1 minus 1, which is 0. Let's test pi over 2. There you go. So the cosine of pi over 2 is 0, so we're left with 1. Let's do 2 pi over 3. That's going to give us -1/2, so it will bring us to actually 2, 1 plus 1. And then let's test pi. The cosine of pi is -1, so we have 1 minus 2. I'm sorry, 1 plus 2, which will become 3. Okay, so now we can plot those points. I see that the largest R value we have is 3. And then we can use reflection to find the rest of the points. So we have 0, which, like I said, is usually right here, but since it's moving in the opposite direction, 0, 1 will actually fall right here. Then we have pi over 3, 0, which is at the origin. And then we have pi over 2, 1, and then 2 pi over 3, 2, and then pi 3. Now we're going to reflect, so I'll reflect this down to here and this to here. So looking at this, it might be like, wow, what's going on here? But if we remember that we're going to have that inner loop, we can kind of use that to guide us. So to create the inner loop, it's actually going to come through like this. There's the inner loop, and that's what your graph is going to end up looking like. So when you expect that inner loop, you can see why we have a point here and here. And then you can kind of connect the dots to make your nice inner loop limestone. All right, go ahead and pause the video and give this problem a try. Okay, here once again, notice the points that I chose to use. I used points in quadrant 1 and quadrant 4 because I know it's going to reflect left to right rather than up and down. So once again, we know that we have an inner loop. So when we plot our points, we kind of can use that knowledge to guide us when we're connecting the dots. Okay, so now let's try a different type of curve. We can see that this is actually going to be a rose curve. And remember, when your n value, which is 3, when n is odd, it's going to actually tell you the number of petals. So I see that n is 3, so I'm going to have 3 petals. And I see that my a value is 2, which is essentially going to be the length of my petals. So I'm just going to draw 2 circles. These are actually really, really quick and easy to graph. We can check 1 point just to see where we can start. So if I plug in 0, the cosine of 0 is 2. So we have this point at 2, 0, which tells me that I must have a petal right here. And if I know that I'm going to have 3 total, and I know that they're evenly spaced, and also that my curve is going to be symmetrical about the polar axis, I can kind of use logic to determine that my other 2 petals are going to be right here and right here. But of course, you could always plug in a few more points to check. Okay, go ahead and pause the video and give this one a try. All right, for this problem, we have 3 petals again, but now we have sine, which needs to be symmetric about the line theta equals pi over 2. Now, I tested 1 point. When I plugged in pi over 2, the sine of 3 pi over 2 is negative 1 times 2 is negative 2. So although pi over 2 is up here, it's moving the opposite direction. So as soon as I know that I have this point, I know that I must have a petal right here, which means my 2 remaining petals must be here in quadrant 1 and here in quadrant 2. All right, let's try one more together. So here we can see that we're going to have another rose curve. And this time our n value is 2, which means the number of petals for this curve is actually going to be double that. We're actually going to have 4. And our a value is 3. We also know that our graph should be symmetric about the polar axis because it involves cosine. So I'm going to give myself 3 rings for my graph. You can check a point if you would like. Once again, we can use 0, and then we'll get 3. So this point at 3, 0, which means I must have a petal here, which means that I have to have a petal here, here, and here. So our graph is going to look just like this. All right, go ahead and pause the video and give this one a try. All right, let's have a look. This one, we're actually going to have 8 petals. We're still going to have one that starts right centered around the polar axis. But to fit it in, we're going to need to have 4 here and 4 here. And you can see that our graph is still symmetric about the polar axis. All right, now let's try this last type of curve. This is going to be a lemniscate. And this is pretty much a dead giveaway because we see that r squared. So remember in the formula that we saw, this value is a squared, which means that our a value is 3. So I'm going to give myself 3 rings And you just have to remember that the lemniscate for the sine equation, it's going to fall in quadrant 1 and in quadrant 3. This is the only one that kind of breaks that rule for symmetry, but this is exactly what it looks like. And remember, this distance, the length from here to here should match your A value. All right, last problem. Go ahead and pause the video and give this one a try. All right, once again, we have a lemniscate. Here our A value is 2, and since it's cosine, we know that it falls right, centered around your polar axis. Okay, that is all for today's lesson. Thank you for watching.